Need focus. Focus here. Focus on me. Come on, focus. There we go. All right. Sorry about that, everybody. I was having some technical difficulties, but I fixed them. So that's a plus. Fixed my technical difficulties. And I need to get my iPad because we're going to do some math today. I wanted to make sure that we took some time and answered some questions, and also get some learning in, learn a little bit more about some of the math side of the business when it comes to transformers. I'm focusing on transformers, but what we're going to talk about today are pretty generic. So Steve Froming, I see Steve Froming out there. I see David Engelhard, Michael Hofkin in the house. Thank you, sir. I see Steve Froming. So thank you. And I'm a little bit just trying to make, because I had to reboot some things, but I believe I am good now. So I just want to make sure that I am good. Okay, so let's do this. Today, we are going to talk on IAEI News Live. Hey, Freddie B, thank you. Today on IAEI News Live, we're going to talk about transformer calculations. We're going to get to the math, and it all starts now. All right, you thought I was gone, didn't you? Okay, so I want to... All right, yep, that's working. All right, I just want to make sure that everything was working fine. Okay, everybody, listen, this is what we're going to do. I am going to put this in dark mode. I'm going to put this in dark mode, and I'm going to put the grid on. And we're going to do a little bit. Let me just make sure this works. T-E-S-T. Look at that. It works. All right. Just wanted to make sure that that worked. All right. So I'm going to need you to get your calculators out. And I'm going to open my calculator here. I'm going to zero it out. And I'm flying by the seat of my pants here, but we're going to float between two things. I have my talking paper here on my iPad. It's my talking paper, and then I'm going to basically do some diagrams of a delta Y ground transformer. Hey, Nihad, I know. Sorry about that, buddy. I was about 5 minutes late, so I'm catching up here. So I want to do some diagrams. We're going to do here's what we're going to do. Look at that. Hey, it doesn't look too bad. We are going to do I need my spectacles. Get your spectacles, because we're going to do a 300 kVA transformer. 300 kVA transformer. It's a 480 volt primary to 208, 120 in a delta Y grounded configuration, probably a very common configuration that we see. Now, what I want to do is I've done this in the past, where I talk about, hey, Don Ganir, you're gonna love this, buddy. So I have done in the past, I reflected currents from the secondary of a transformer to a primary of a transformer, three-phase bank. And I talk about the turns ratio being, say in this case here, of a 480 to 208. I'll say that my turns ratio is 480 to 208. So I will take the secondary full load amps, multiply it by 208 volts, divided by 480 volts, and that's my primary. And so what I want to do is I want to walk through that calculation, because I've had people tell me they don't agree with my math. And the comments that I've received are generic in nature. They never get to specifics, because I'm like, well, if I'm doing something wrong, I want to know. So I decided I'm working on another video as well to go through this, and I thought, you know what, I'm just going to have this discussion in the open, and we're going to run through some calcs. So if I'm going to draw a delta Y ground transformer pictorially, I do that, right? That's my delta side. And in here, I'm going to do a copy and paste. And to get my Y side, to get my Y side, I do this. It just makes life easier. And then I delete. All right, so now I got to draw my coils, right? So these are my windings. These are my windings. I'm not gonna worry about how pretty it is. Those are my windings, and then I have my phase conductors, my phase circuits coming out of my transformer. And I got to draw the neutral, because we're going to talk about the voltages in a second. So there's my A, B, and C. I'm not going to label them A, B, and C either. I am just going to draw them. I'm not going to get into the details, because that would be left for a different day. All right. So here's my transformer. That's my delta Y, and I'm going to do my voltages. Now, basically what I have, and now I'm going to draw 3 separate transformers. I have transformer 1, transformer 2, and transformer 3. Transformer 3 has a little winding issue, but we're not going to worry about that. Anyway, so I have 3 separate, remember, a 3-phase bank of transformers are 3 separate single-phase transformers connected together. And in this case, the primaries are connected in delta, and the secondaries are connected in Y. So if I do the delta connection, I would connect these sort of like this, right? So that's my delta primary side, right? So each one of these points is right in here. So I've got the 2 windings, these 2 windings, so say 1 and 2 and 3. So I got maybe 1 and 2 and 3. I've got 1 and 2 tied together at the same point, 2 and 3 tied together, and then 1 and 3 tied together. So you see sort of how that lays out, right? I'm just going to delete those. Now we know if this is a 300 kVA bank, we know that each of these, and I'm going to change colors. I'm going to use red. We know that each of these is what? 100 kVA. 100 kVA. 100 kVA. So for a 3-phase bank, 300 kVA transformer, each transformer is 100 kVA. And I know I have on the primary, we're going to use a different color. We're going to use green for voltages. We know we have on the primary, across the primary winding, 480 volts, right? So this is 480. 480. 480. And we know that on the single phase side, now, we have line to line and line to neutral. Now I want to have a discussion about voltages. I have to determine I have to figure out, Dawn, Hey, Lou Petrucci, thanks for joining us. So, Mr. Ganir, you are a very smart individual, and as everybody is, but I'm going to pick on you because I love you. The difference between the phase voltage and the three-phase voltage is what? Square root of 3. Right? So I'm going to talk about this square root of 3 a little bit. I'm going to stick that over here. Square root of 3. Very important number. If I start with a voltage of 208 volts, phase to phase, what's the line to neutral voltage? The line to neutral voltage is 208. So V line to line is equal to V line to neutral times I just erased this. Okay? Times the square root of 3. So V line to line is equal to V line to neutral times the square root of 3. If I know line to line is 208 volts, so I know line to line is 208 is equal to V line to neutral times the square root of 3. So V line to neutral is 208 divided by the square root of 3. And what is that? 208 divided by the square root of 3 is 120.0889. So if I start with 208 volts, my voltage single phase is 120.0889. And then so over here, this would be 120.0889. Now, if I said my voltage, hey, Robert from Omaha, booyah! I did not get your email. I will look for it. And Larry Griffith, thanks for being in the house. I'm not putting in a 30-degree phase shift. That will be on the inside. So my 30 degrees shifts are going to be inside. So I have to put my angles in. Remember, each of these are 60, 60, and 60. But I'm working with magnitudes now. I'm trying to understand the primary and secondary voltages. Now, if I'm at a 208 volt secondary, I don't have 120 line to neutral because the square root of 3. If I assume each of these transformers is a 480 to 120 period, then I'm not working with 208. I'm working with 207, 120 times the square root of 3. 120 times square root of 3 is 207.846. So 207.846. It's either 208 or 207.846. And the reason I want to establish, I'm spending time on this, Dawn, is because if you're doing voltage, if you're using primary and secondary voltage to transfer currents from secondary to primary, depending upon how you do this, I've had people tell me I have to use a 4-to-1 ratio. Always, because the turns ratio for this bank of transformers is a 4-to-1 ratio. And my argument is no, it's not a 4-to-1 ratio. It's a 4-to-1 ratio for each individual single-phase transformer, but it's not a 4-to-1 ratio for the transformer bank. especially on my delta to Y ground system. Okay. And Dawn will throw in the 30 degree. I don't think we're going to get to it this time. Maybe next time we'll look at the phase angles, but I think phase angles are a little bit kind of tough right now. So I'm going, now when we think about our transformer full load amp calculations, I'm going to delete this. Now, what is the calculation we use for transformer full load amps? Full load amps is equal to what? kVA, three-phase, divided by the square root of 3 times voltage line. The heck was that? Line to line. I just heard, sounded like a rattlesnake down here. I don't think I've got a rattlesnake down here, but it did sound like one. Anyway. I think it's my speaker. Turning my speaker off. Okay. So kVA three-phase divided by the square root of 3 divided by the line-to-line voltage. And where does that come from? If I take kVA three-phase, and I've done this before and people don't like when I do this, but it helps us understand. Divided by 3. kVA three-phase divided by 3 gets me to 3 single-phase transformers. So a 300 kVA bank of 3 single-phase transformers. 300 divided by 3 is 100. I have 3 100 kVA transformers. All right? Follow me here. Now I need to get a single-phase voltage. And how do I get my single-phase voltage? I take voltage line to line and divide it by the square root of 3. But because the square root of 3 is in the denominator, what do I do with this puppy? I move it up here. So when I move it up there, I'm going to move it up. I have the kVA three-phase times the square root of 3. I'm going to change that to kV. And divide that by 3, divided by the kV line to line. But the square root of 3 divided by 3 is equal to 1 over the square root of 3. Let's do that. Square root of 3. 3 square root. 3 divide. I do 1 over is 1.732, which is the square root of 3. So I can replace this 3 in the denominator with the square root of 3 and get rid of this. And there's a reason I'm doing this. Now, the reason I did that was because to get the line to neutral voltage, I'm taking the 208 volts and dividing it by the square root of 3. And that means that when I do that, 208 divided by the square root of 3 is 120.0889. It's not a solid 120 volts. 0.0889 makes a difference, and I'll show you why it makes a difference in a second. So now, what I want to do is I'm going to calculate the full load amps on the secondary, and then we're going to reflect it to the primary. And we're going to reflect it to the primary using 2 methods. One, the method I always use, 480 over 208 as my turns. And the second, we're going to use 480 over 120. And I'm going to show you what you need to do if you're going to do that math. All right, so if I'm working this out, I've got 300 kVA divided by the square root of 3 divided by the line-to-line voltage on the secondary, kV, is 0.208. So I got 300 kVA, 3 square root divide, 0.208 divide, 832.7167. 832.7167. Let's double check my math. 300 divided by the square root of 3 divided by 0.208, 832.7167. I do my math twice because I can screw things up easily. Okay, so that tells me the full load amps is equal to 832.7167 amps on the secondary. Now, here's what I am going to do. I'm going to calculate my primary full load amps, and we're going to write it up there, and then we'll do the reflection and verify. So I have 300 kVA divided by the square root of 3 divided by the line-to-line voltage on the primary, which is kV 0.480. Why is it 0.480? Because voltage is 480 volts. Kilovolts is 480 volts divided by 1,000. And that's why it's 0.480 kilovolts. So 300 kVA divided by the square root of 3 divided by 0.480, 360.8439. 360.8439. Let's do that math again. 300 kVA, the square root of 3, divide 0.480, that's 0.48 kilovolts, 360.8439. So my full load amps over here, 360.8439 amps. All right, so now we have our full load amps. Now, if I want to reflect, I'm going to use my three-phase method of reflecting my currents. For the three-phase bank, my N1 over N2 is equal to 480 over 208. Now, I'll have people say, no, Tom, N1 over N2 is 480 over 120. And you're right for a single-phase transformer. But for what I'm about to do, 480 over 208 works perfectly. So, if we know this to be true, we know that I1 or I primary is equal to I secondary times 208 over 480. And we know that I secondary is equal to I primary times 480 over 208. And if I do the math, my secondary current, I'm going to erase this. My secondary current is 832.7167. 832.7167 times 208 divided by 480. 360.8439, which is 360.8439. The exact same number. Now, how about the, let's reflect the primary to the secondary. So if I take the primary, 360.84, if 8439, 360.8439, which is right there, multiply that by what? 480 times 208 divide 832.7167. 832.7167. So what I did, and what some people disagree with, is I used the turns ratio of 480 to 208, primary voltage 480, secondary voltage 208, and I reflected my current from the secondary to the primary. I didn't use 480 to 120. Now I could. And we're going to walk through that calculation to understand where that went and why that is what it is. Okay. So we're going to do the single phase, but I just did the three phase. Now we're going to do the single phase. And let me tell you what I just calculated. Let's look at the bottom left-hand side. hold on. I did not connect the secondary yet, and why? So I'm going to do that now. My secondary Y connection is this. That. Now what I did was I calculated 832, we'll call that 832.7 on the secondary, 832.7, 832.7, 832.7. On the primary, I calculated 360.8. 360.8. That's my line phase currents. By using 480 and 208, I'm here. I'm in this conductor. I'm not in here. Okay, that's not where I'm at. I'm actually on the phase conductors before the three-phase bank. So if you looked at this as a black box, you would have phase A, B, and C going into a black box, and phase A, B, and C coming out of that black box. I calculated currents here and here. And it works regardless of the configuration. I don't care if it's a delta, 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 Y, 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 does not matter. I use the line-to-line voltage on the primary, line-to-line voltage on the secondary. And I'll prove that by doing another calculation. After we do this manual single-phase calculation, I'm going to change the configuration to a Y, Y, and we're going to do the exact same math. All right, so now what I'm going to do is I am going to use this, I'm going to do the single phase calculation. Right? So now I'm going to do a single phase. I'm going to draw my line. I'm going to use white. All right, so I'm drawing this. Keep me separate. All right, so if I'm going to use the 480 to 120, now we know the secondary current is 832.7167. So full load amps, we'll call this I secondary is equal to 832.7167 amps. If I do my N1, if I do my N1 to N2 calculation, I'm going to take 832.7167 times 480 over, and I'm going to use this number because I want the numbers to line up. I'm not going to use the 120. I'm going to use 120.0889. 120.0889. All right. So what does that equal to? 832.7167. 832.7167 times, I'm going to go secondary to primary. So it's 120 times 120.0889 times, divide that by the primary, which is 480. 480 divide. 208.33, 208.334. 208.334. 208.334. And I got to change something here. I got this backwards. I want to reflect secondary current to primary. So I've got to take my secondary current times my secondary voltage, which is 120.0889 divided by 480. Make sense? And I'm using the 120.0889 because I want the numbers to match. I could use 120, but I'm going to be off by decimals. Not a big deal, but by decimals. And I'll run that real quick to show you. So my primary current, which, if I go to my diagram here, it's 208.334. If I go here, I calculated this number, 208.334. I'm not calculating that number. If I looked at this diagram, I'm calculating 208.334. That's in the delta. I'm not outside of the delta. This is a mistake you could make, you may make, if you use the 480 to 120. You're only calculating what's in the delta on the primary of every one of these transformers. Every one of these transformers has that same current. But what's flowing here is not the current that's flowing through the primary winding because I'm in delta. So to get my current here, I have to take my 208.3334 times the square root of 3. And if I do that math, so there's my 208.334. If I multiply that by the square root of 3, 360.844. There's my 360 right here. 360.8439844. Rounding error. So I can do my phase-to-phase voltage on the primary, phase-to-phase voltage on the secondary. I can use my 480 to 208 to reflect my secondary currents to my primary. I can use 480 to 120, but I've got to remember, if I do 480 to 120 and I have a delta on the primary, I'm only calculating what's in the delta. I have to add on the square root of 3. Make sense? Larry Griffith, Don Ganir, it's kind of quiet. Robert from Omaha, gotta love the pencil. Gotta love the pencil. So, if you have, let's do another transformer. Let's do a, I don't know. $750 kVA transformer. 480/208-120. What do we have? I'm going to always do this. We're just going to put this in practice. So there's my transformer. It's 480 up here. And this is 208/120. And we know this is 750 kVA. So we'll just do the secondary currents, I secondary. So full load amps on the secondary. is 750 kVA divided by the square root of 3. Divide that by 208. 0.208. 750. 3 square root. Divide 0.208 divide 2081.8, 2081.8. So 2081.8 amps. Now, if I want to know the primary current, I take 2081.79 or 2081.8, multiply that by 208, divide that by 480. 902.1. So the primary is 902.1. 902.1 amps. Now let's calculate the full load amps on the primary. 750 kVA divided by the square root of 3. Divide that by 480. 750. 3 square root, divide 0.48, divide 902.1. Look at that, 902.1. So I can reflect secondary. Now that works with, even if I take a load amps, it doesn't have to be the full load amps. If somebody told me they had, somebody said they had 800 amps flowing on the secondary, what is the equivalent primary current? I would take 800 times 208, divide that by 480, 346.7. That would mean I have 346.7 amps on the primary. Why might that be important? I might want to do selective coordination. I might want to know what will my upstream overcurrent device see for a secondary current of that value on a load current. The transformer will transform the current on the secondary to the primary based upon the turns ratio, which is that line-to-line voltage, line-to-line on the primary to line-to-line on the secondary, and 3.997 to 1. Yes, there you go. That's your 3.997 to 1, which is an odd number, right? So divided by the square root of 3. Exactly, Dawn. So, okay, now let's do this. Let's take this same transformer, let's take that 300 kVA transformer, 480 Y to 208 Y. Okay, so we're going to do, I'm going to use my white pin. Ooh, what do you think, Dawn? Isn't that pretty? Here's my winding. And I'm going to do the same thing over here. This is why I think it's easier to do it with a triangle and then do the inside. All right, so I know I'm 300 kVA. And I know I'm 480. So if I'm 480 line to line, this is my 480. What's my line to neutral? Is 480 over the square root of 3. 480, 3, square root, divide, 277.128. So 277.128 across each of the primary transformers. And if this is 208, we already know this is 120.0884. what was it? 889, 1.0889. It looked like a 4, right? So 480 line to line on the primary, 208 line to line on the secondary. My line to the center point neutral is 277.128 on the primary, 120.0889 on the secondary. And I know I have 3 100. So if I'm going to do this, I'm going to copy this. Copy. Paste. All right, so my individual coils are no longer 480 to 120. My individual coils are 277.128. 277.128. And hence, Don, now my square root of 3, or Dan Harwich. So 2.31 to 1. Always love students' reaction to that ratio. I know, it's exactly right. And that's why people think it's wrong. But it's not, because of that square root of freaking 3. So now I've just did this in delta or YY instead of delta delta, but you've got to understand what your voltages are and where you're measuring your voltages. And if you establish 480 as the number, then your line to neutral is not 277. It's 277.128 because of that square root of 3. You can say, well, it's 277 because we're power systems engineers. We don't care about that 0.128. That's the other part of this. So you have your mathematics. This is why when I first came out of college, I worried about the decimals because they mattered. And not enough for a power systems engineer, because it's like, well, 277, 278, who cares, right? 277.1 versus 277.9. Whoopie ding ding. But to the student who's looking at the numbers, if I would have said, let's do this. If I would have done my turns ratio, well, I'm going to do this 120. So I'm going to do 120. Well, let's do that. Let's do this. If I said this was 120, my line-to-line voltage, forget it. I'm just going to go back and continue my single phase discussion. You'll get it. We'll do that later. So those are my ratios. Now I have 100K. I'm going to do this based upon the single phase transformer. I have a 100 kVA transformer. To get to the full load amps on the secondary, I don't divide by the square root of 3. I don't divide by 3. It's a single phase transformer. It's 100 kVA. I have to divide it by the voltage, which is 120.0889. 120.0889 divide. I've got to multiply that by 1,000 because it's kVA. It's not 1 kVA. It's not 1 VA. It's 1,000 kVA. So I have 100. Or it's 100 kVA. So it's 832.7164. Well, that number sounds right, right? 832.7164. 832.7164. We've seen that number. Now I'm going to transpose it to the primary. But remember, I'm in Y. And I'm not working on 480 volts. I'm using 277.128. So if I want to reflect 832, so if I want to say I primary is equal to 832.7164 times the secondary voltage, 120.0889 divided by 277.128. Not 480, because my coil is 277.128. The voltage across the line side of that transformer. I can't use 480 now. Make sense? So let's do that math. 832.7164, 832.7164 times 120.0889. And I need to divide that by what? 277.128. 277.128 divide 360.8441. So 360.8441. That's my primary current, which is right there, because it's no longer a delta, it's a Y. So 360.8441. Now, Dawn, I'm going to take I primary, and I'm going to take 832.7164 times the secondary line-to-line voltage, 208, divided by 480. I'm not going to worry about all the decimals. 832.7164, 832.7164, enter. 208 times 480 divide 360.8438. Yes, it's the same number. But I didn't have to worry about the decimals. Now, if I would have used 120 to 277, 120 to 277, 832.7164. 7164. I'm going to use 120, 277, divide 360.74. Now there's a difference. Instead of 360.84, it's 360.74. A power systems engineer does not care, right? Because you're talking 0.1 volts difference. You're going to end up saying 361 if you want to err on the side of the higher voltage, right? Or 360 if you just want to ignore anything past the decimal point. You're in the ballpark on voltage or current on current. You have 360 amps versus 361 amps, whatever. So the math makes a difference. Understanding the configuration, using the right voltages makes a difference. You can stick with the rounded numbers, the 120 versus 208. You just saw the difference. I'm 360.74 instead of 360.84 by simply using 277 and 120. The error in difference is negligible. But if you want to do what I just wanted to do today, was say, look, they are equivalent. Both methods. If you want to do the single phase, you can. You've got to think about the configuration on the primary. Is it a delta on the primary? And what is the current you're actually calculating on the line side of a single phase transformer when you take that method, if you're not going to use line to line on the secondary, line to line on the primary? And it doesn't matter if it's a delta Y, delta to Y, if you're using line to line voltage on the primary, line to line voltage on the secondary. It's a screwed up turns ratio, right, Dawn? 3.997 to 1. 2.31 to 1. These things are screwed. The ratio, if you do the math, N1 over N2, primary voltage over secondary voltage, the numbers don't look right. It's because of the square root of 3. But when you're dealing with a three-phase bank of transformers, it's a little bit different of the beast because of the square root of 3. So, there was another, what was the other one? I did delta Y ground, I did Y to Y, we did it single phase, And so if I just said, let's do this. If I did this with 120 volts, remember we did 120.0889 and we calculated 208.334. If I just did 120 over 480, so 832.7167, 832.7167, 832.7167. This is why you got to do the math, boys. Enter times 120 instead of 120.0889 divided by 480. I get 208.1792. So this number here becomes 208.1792. And then I have to multiply that by what? The square root of 3 to get the current on the line side, because that's just what's through the primary and a delta connected. So I've got to multiply that by the square root of 3. 3 square root times 360.57. So now I am at 360.57. Here, 360.57 instead of the 360.8439. Now that's a little bit, it's 0.3 amps difference, okay? And you might go, well, that's a big deal. You might say that's a big deal if you are, if you're rounding up versus rounding down, because you went from, well, I'm still 0.57. You're still at 361, okay? Because you're above 0.5. But if I would have done that example and used 120 and not used 120.0889, and I would have come up with 360.57 instead of 360.8439, somebody out there would have said, well, that's why the math is different. That's why you can't do line to line to line to line, which would be wrong, right? So what I've tried to do in that example is give you a little flavor for an easy way to do. You calculate the full load amps on the secondary or the primary, whichever, and just reflect the current to the primary. So Robert from Omaha, yes. Steve Cavaleris from New York in the house. Thank you, Steve, for joining us. All right, so Larry Griffith, thanks, buddy. So it's getting back to the math is important. Okay. Getting back to the math is very critical and very important. And we can build some shortcuts in. From secondary to primary, etc. But we have to understand the details. Devil's in the details. In my opinion, devil's in the details. You got to be fully aware of where you're at and where you're going. And when you're going to start doing the math like this, it can get confusing very quickly when you're dealing with deltas and Ys. And then maybe next time, Dawn, we'll get into that 30-degree phase angle and the shifts and the and also understand where that even matters, right? But that's some basic math around primary and secondary. And we went through calculating the full load amps of a transformer. So we killed a couple birds with one stone, or broke a few windows with one stone, and did all that jazz. Now, I said this last time that I would answer some questions. Let's take a look at some comments. I remember I think one of the questions came in from David Engelhart. He said, curious, this YouTube channel remains to identify the acronym IAEI as the International Association of Electrical Inspectors. Now, thank you for that note, David, because I asked the team down in Texas to make some changes, and they did. So now we have fixed and cleaned up some things over here. We have the Independent Alliance of Electrical Industry, and we have cleaned that up. So we aligned, they made some changes to our about information. So thank you. The acronym, or we are still the Electrical Enforcement Authority, so that is not changing. So they did clean up some of the verbiage because this did have some errors in it. So thank you for bringing that to my attention. Right, Dawn, 0.08% does not matter in the real world. But by going through those decimals, I think I did two things. I helped with an awareness that we're not talking about just flat numbers. Right? It's not 277. If you're dealing with 480 and you're going to divide by the square root of 3, it's not just a straight 277. And if your primary is 277, or say your primary winding is 480 volts, then your line to neutral is not going, or your secondary is 208, your line to neutral is not going to be exactly 120. So when you do the math, but I agree with you, 0.08% doesn't amount to a hill of beans. All right, so let's look at another question. Is the first draft available for download? That was during my first draft report for 2020. Oh, that was 2023. It was 2026 code cycle. The first drafts are not available for download yet. You can get the www.nfpa.org/70next. There is the next edition. You can see that the public input closing date and the first draft posting is going to be July 10th, 2024. So the first draft posting date is July 10th, 2024. The public comment closing date is August 28th. So those are your dates. So in July, look for the first draft to be posted for the 2026 edition. We had SBDC9QB say the light does turn off when you shut the refrigerator. There's a plunger switch at the top of his. So thanks for doing that investigation. Is it permitted to comply with 210.12A5? This is Justin Solis, 1953. Is it permitted to comply with 210.12A5 for a portion of the branch circuit and 210.12A6 for the rest of the circuit and still be compliant? 95% of the conduit from the breaker to the first AFCI. So what he is saying, this is a good question. Hey, thanks, Dawn. This is a good question, Dawn. This gentleman is saying Control C. Hopefully I can put it here. Paste. Allow paste. Okay, so here's what he's saying, Dawn. Is it permitted to comply with 210.12A5 for a portion of the branch circuit? So if I have my panel board and I have my breaker Say this is an AFCI. No. This is just a standard thermomagnetic breaker. We'll do this. And that's the OBC AFCI. And let's say that he says 210.12A5 is if metal raceway, metal wires, and metal guns. So this is MC. And then 6, where a listed metal or non-metallic conduit or tubing or type MC cable is encased in not less than, so this is 2 inches of concrete for the portion of the branch circuit between the branch circuit overcurrent device and the first outlet. Wow. So what he's saying, this is a good one, is it permitted to comply with 210.12A5 for a portion of the branch circuit and 210.12A6 for the rest of the circuit and still be compliant? When I look at the language, here's the issue. The language says, if metal raceway, metal wireways, metal auxiliary gutters, or type MC or AC cable meeting the applicable requirements of 250.118 with metal boxes, metal conduit bodies, and metal enclosures are installed for the portion of the branch circuit between the branch circuit overcurrent device and the first outlet. So this diagram, that cable is, there's your first outlet. Dan, thank you. Happy birthday. Thank you. So, you know what? And the way I read the second part of this, the number 6, where a listed metal or non-metallic conduit, I'm not getting the whole thing, where a listed metal or non-metallic conduit or tubing type MC cable is encased in not less than 2 inches of concrete for the portion of the branch circuit between the branch circuit overcurrent device and the first outlet. So in both of these cases, it says between the branch circuit overcurrent device, which is there, and the first outlet, there's no provision in 210.12a that would permit coming out of the panel board in MC cable, going into 2 inches of concrete to the first outlet. That would not be. Now, your AHJ could say, look, I'm going to permit that, but that's not a specific allowance in the code book. So I look forward to your public input. That's a good question. And I believe it's something that has to be looked at. So very good point, and that's why we do this. That was a very good question from @Justin Solis 1953. @Justin Solis, I look forward to your public input. All right, so we at least got to a couple questions. I'm going to start adding these on. Killer Bees, thank you. Michael Hopkin in the house. Smash that like button. I saw your email, Michael. I will get back to you. Thank you for everything, everybody. I think we're in gear. I think we're in gear. I like it. That is a really good question. Justin Solis, 1953. Very good question. And hopefully you'll make some public inputs. I'm not sure we can fix it in the 2026 code cycle just because it would be new material in the second draft. But a combination of 5 and 6 may work. May work. All right, everybody, I'm going to start looking at these questions and bring them into the Tuesday sessions and answer of at least a few of these as we go. I'll look at the newer ones. That one is a month old, but it was a good question. And I will keep going down through these comments and questions, and I'm going to look specifically for the items that need to be addressed. All right. Fred, I think you're right. And I think that it depends on how that is routed. If there is a junction box there, then that would be your first outlet. But if it's a continuous run and you just happen to go into a raceway, Fred, that's why I say I look forward to the public input, because it needs the entire committee review. Nihad, yes, my Easter break was Sunday, so it was a good day. It was a good day. Thank you, everybody. Thanks for joining in. I appreciate everybody joining in and driving our membership. Our YouTube channel is moving up in the world. Our YouTube channel, if I go to YouTube Studio, we broke the 2,000. We're at 2,165 subscribers. So thank you. 182 subscribers in the last 28 days. I appreciate everybody's attention and subscriptions to the IAEI's YouTube channel, growing our YouTube presence, bringing value to our members. Thanks for everything. Thanks for what you do for the electrical industry. Thanks for what you do for electrical safety. Remember to stay safe and please stay healthy. We'll see you next week.